Okay, thanks for coming back. So today, so at the beginning of the first part of the talk, will be focused on constructing negatively curved metrics. And the technique is commonly known as the Farrell-Jones warping method. So let me first state the main application, which is the main thing we care about. And then we'll see a more technical statement of the warping method later. So this is a theorem of Farrell and Jones. So M will be a closed hyperbolic manifold, as usual. And sigma, as usual, will be a homotopy n-sphere. And the statement is, so given epsilon greater than 0, there exists some constant r, which depends on epsilon and the homotopy n-sphere, such that if the injectivity radius of M is bigger than R, then M connects some sigma has a metric, Riemannian metric with curvatures pinched between -1 minus epsilon and -1 plus epsilon. Okay, so the injectivity radius, this is the radius of the largest isometrically embedded ball that you can fit in M. And so the theorem says if that's big enough, then you can put a negatively curved metric. And the metric can be as pinched as you want as long as the injectivity radius is large enough.
Sorry, so
yes?
Here we don't have the n greater than 6. This will just be true whether it's hyperbolizable.
Yeah, so let me first maybe a warning. So that's a good comment. Well, if M connects some sigma is diffeomorphic to M, then, well, the theorem, I guess, is boring. Because then you're already hyperbolic, and you already know you have a hyperbolic metric. Right, so I mean, this is important for the ultimate goal of constructing exotic negatively curved manifolds. And so, well, the second part of today, I'd like to start to address. We'll need to understand when this happens or doesn't happen. A second remark is that this injectivity radius condition can always be achieved in a cover. So any M has a finite cover with the injectivity radius bigger than R, if you fix R at the beginning. And this can be seen from the fact that the fundamental group of M is residually finite. So I'm going to put this in the exercises. Oh, yeah, thanks. In the cover. Yeah. Okay. So that's the statement. Any questions about the statement or anything so far? Okay, so mark / exercise. So now let me start by informally discussing the strategy, which begins by choosing a particular model for M connects some sigma. So remember, yesterday we saw that any homotopy sphere can be constructed by gluing two disks by some diffeomorphism of the n-1 sphere. And so then we can write M connects some sigma in the form in the following form. So the connect sum, you just remove a ball from each and then glue. But given this expression, well, you can think about removing this ball and then, well, right. So you remove a ball from M and then you glue it back by this diffeomorphism phi. Okay, so let me draw a picture of M connects some sigma, which will guide us in constructing the metric we want. Well, here's first maybe a picture of M. So we're going to fix a point P, which would be a base point. And okay, so and P maybe is chosen with large injectivity radius. And then okay, so right, so this is meant to indicate the sphere of radius r. And this is going to be the sphere of radius 2r. R will be some parameter that we choose later to be large. And then, okay, so let's see. So this up to here is just going to be a ball, and we'll glue this boundary component by this diffeomorphism phi, and this one by the identity. Okay, so is that fine? This is just a picture of M connects some sigma. The interesting gluing is happening here. And right, so the picture of the metric that we ultimately will construct, it's going to be hyperbolic near P and hyperbolic very far from P. And then here's where we're going to make some change. So we're going to change, I'll just say change the metric here. And let me just record for later use that, so the metric in polar coordinates at P is a warped product, so it looks like this, where sigma 1, this is the unit sphere in Rn. Okay. Any questions about that? All right, so this picture and this strategy ultimately is going to allow us to reduce to studying metrics just on an annulus here. So metrics on Sn minus 1. So it will be helpful to have a fixed annulus to work with. So let's just consider Sn minus 1 times the interval 1 to 2. And, well, OK, so I just want to look at metrics here. Oh, yeah, so maybe the first observation is given a metric on this annulus. We can insert it into M connect some sigma via the following composition. So we can push forward the metric in the following way. Yes. I want to say M or M connects some sigma. Yeah, I mean, let's say M. Well, OK, yeah, let me say it this way. So this map is sort of the obvious map where you just multiply by R. It's helpful to think about this as the sphere or as an annulus in the tangent space at P. OK, so this is just scaling the annulus. And then this is the exponential map. And well, not any metric that we put here is going to glue in nicely to give us a smooth metric on M. So the gluing constraints are as follows. So on the left endpoint, we should match with the hyperbolic metric on the sphere of radius r. So that's sinh squared r times sigma 1. And on the right endpoint, we should see well, the pullback of the hyperbolic metric by this somewhat mysterious map phi. So we should see phi star of sinh squared 2r sigma 1, which is the same as sinh squared 2r times phi star of sigma 1. Just pull out the scalar. OK.
So in the end, phi will be an isometry.
Yes, phi will be in isometry from the metric we put here to the yes, I mean, right. we want the two metrics to be isometric so that the gluing will be at least continuous. And maybe technically we should choose the metric to be sort of constant near the boundary so that it glues smoothly. Okay. All right, so now here's a construction of the metrics that we'll ultimately use. So let's start by defining beta t as follows. So these are metrics on this annulus. No, so sorry. The first thing is not quite that. This is just a path in metrics on Sn minus 1. It's just the straight line homotopy between the round sphere and the round sphere pulled back by phi. And then we'll define B. So this will be a metric on the annulus to be beta t plus dt squared. Okay, it's a metric on this annulus. And then, right, so this metric doesn't quite have the right gluing property. So for r greater than 0, we'll define beta, or b r. Bar is the notation I'm going to use as sinh squared r beta t plus r squared dt squared. Okay, so this metric, this satisfies the gluing constraint. So for any r, we can insert this metric here and get a nice metric on n, m connects some sigma. And shortly, we'll want to understand when this metric will be negatively curved. But maybe let me just say as a sanity check that if beta of t is just identically the round metric, then this beta bar r is a hyperbolic metric. Okay. Okay, any questions about the construction? Anything so far? Yes?
So here, you don't really need the injectivity radius to be large everywhere, just at peak.
Yeah, ultimately we're just going to use one point with large injectivity radius. Yeah.
But you need like a lot of symmetry around theta. I mean, that's why you need it to be hyperbolic, for example, and not complex hyperbolic.
Well, yeah, so there are variations of this method which do put, I think there's a variation in the complex hyperbolic setting. Yeah. Okay. I mean, I think well, it will be helpful in a second that this warping function is explicit. All right, let me write now the technical statement that we will prove this theorem. So I'm going to call this theorem 1, and this is theorem 2. Yeah, so the statement is for any metric B of this form, so on Sn minus 1 times 1, 2, we define BR bar as above. I wrote this is the wrong expression, RT. So then, given epsilon greater than 0, there exists a capital R so that if R is bigger than capital R, then the curvatures of BR bar are pinched near -1. Okay, so theorem 1 implies theorem 2. Once we have this metric that glues smoothly and it has a negative curvature on the annulus, and then the curvature was already hyperbolic everywhere else, so it's negative everywhere on M connects M sigma. Okay, so, well, the proof of theorem 2 is, at the end of the day, a technical computation. So I'm not going to give you all the gory details, but let me try to give you some intuition for why you might believe that this is true. Okay, so this is intuition for the proof of theorem 2.
Sorry, Bena.
Yes?
But you don't really need theorem 2 to prove theorem 1, right? Yeah, I mean, you build this back, I mean, this BR bar on the second column, and that will be enough, right? Like if you show that particular choice has negative curvature for large enough R, you will be done, right?
But that's what theorem 2 is saying.
That's a strong
Yeah, that's right. Yeah.
I don't know if it's different in this case, but for the Gromov-Thurston example, the calculation you have to do, you may as well just prove this. So
Mm-hmm.
There's no difference. It could be true.
Okay. All right. So, so intuition. So the first bit of intuition is that if R is very large, then beta t, this interpolation, the straight line homotopy, happens. Well, so well, okay. I mean, this is okay. It's intuition, so it's an informal statement. It happens slowly. Okay. So this is not to scale, of course, but so this. We have this one fixed path, but then we're varying R. And the bigger R is, the longer this annulus is where we're interpolating. And so the slower that the interpolation happens in terms of T. Okay? So then, right. So, okay, so now I'm going to make a simplifying assumption. So let's, all right, pretend that R is so large that beta t is locally constant. Okay, this it almost hurts me to write it because it doesn't make any sense. But just imagine R is gigantic, and then like for very small t, beta is not changing at all. So let's just say it's constant. Okay, and now we can do a computation. Okay, so now we apply, from last time, the Bishop-O'Neill formula. To this metric, alpha, which is sinh squared RT, beta plus R squared dt squared. Okay, so this is a word product metric. Okay, and the Bishop-O'Neill formula gives us the curvature for such a thing. So let me remind you how that looks. So it's the curvature of a two-plane spanned by these vectors is given by this formula. Where here f is the function f of s is sinh s. Okay, now we can just compute. Okay, so second derivative of sinh is sinh. So this first term just becomes minus norm y squared. And then I'm going to split up the second term into two pieces. So f is sinh. So sinh squared RT plus so this is cosh. Okay, and then this term, we saw this computation last time. This term is minus 1. And so we get minus. Okay, now we're almost done. Almost done. So these two are orthonormal in this expression. So this bit is minus 1. And right, so now we just need to think a bit about this expression. So beta here is just some mystery metric on the 2 sphere, or on the n minus 1 sphere. So we don't know this value, but at least it's bounded because the sphere is compact. So Sn minus 1 compact implies that k beta x1, x2 is bounded. So the numerator is bounded, and then as r goes to infinity, the denominator goes to infinity. So this whole expression goes to 0 as r goes to infinity. Okay, so this goes to 0 as r goes to infinity. Okay, so that's what I'm going to say about the proof of theorem 2. So there's two kind of morals of the computation. One is, so basically you can achieve negative curvature by one, interpolating over a really long region, and two, choosing that region to be very far away from the base point. Okay, so you want this annulus to be far away from P and to be really long. And those two together make the computation work. All right, questions? Yes?
Is it possible to write some estimate for R into this function R,
Right. So for this R, I mean, the thing is, I think you need to understand what this gluing map phi is. I mean, maybe if you can understand something about this phi, you can write something down. But I mean, even in the Gromov-Thurston, can you get some explicit control? Do you know on R? You do.
Paper, they give some
Oh, I see.
stuff.
Okay. Yeah. Okay. Right. Yeah, I think understanding phi is the difficulty there. Other questions? Comments? Okay. So let me make one remark, and then we'll have a break. And then the second half will be something different. So the remark is, so I'm just going to mention, so these are other applications of the warping method. Well, there's lots of them. But let me just mention two. The first one came up, it came up last week in Jean's talk. And I think I mentioned it yesterday as well. So it's a result of Antoneta that says that Charney-Davis strict hyperbolizations so Jean defined that in his talk last week. I won't say what it means here. Well, some of them, have negatively curved metrics. And the point is that the strict hyperbolization construction, it gives you like a singular cap -1 metric, but there's definitely singularities. And Antoneta shows that you can smooth the singularities by some warp, using the warping method. Yeah, and it's quite technical. Okay, the second thing I want to mention is a result of Farrell and Antoneta. Which is that, so the Teichmuller space or moduli space of negatively curved, or you could even say pinched, negatively curved metrics on a closed hyperbolic manifold is not generally contractible. Right, so let me just say something slightly more precise. So the Teichmuller space of, say, pinched negatively curved metrics on M, this is defined as all of those pinched curvature metrics up to diff naught, the diffeomorphism's isotopic to the identity. So similar to what you do for surfaces. But here epsilon means epsilon pinched, like over there. And they show that for n at least 6, if theta n plus 1 is non-trivial, then pi 1 of this Teichmuller space, well, you can find examples where this pi 1 is non-zero. And again, a key component of this is to use the warping method to put strange negatively curved metrics. Okay, so let's take a break now. I think Misha suggested we take like a 15-minute break, and then the talk will go to like 12:15, so that we can avoid the lunch mayhem. Yeah. Okay, so let's continue. So the second part of today will be about what's called smoothing theory. So the basic and general setup, this won't need to be a hyperbolic manifold for now. Let's take it to be a smooth manifold. And then let's consider boldface M of M, which would be the moduli set of smoothings. So this will be the set of smooth structures on M. So smooth atlas up to diffeomorphism. And, well, essentially, we're motivated to understand something about this set. Basically, we would like to know if M is closed hyperbolic. Then our M connects some sigma, and M, well, maybe, are these different elements. Or when does this happen? Right. So in general, this is a hard question. And maybe to temper your expectations, just remark that so there's no closed hyperbolic n manifold, n at least 4, for which like the size of this set is known. Okay, so like basically last time I told you that Crevera and Milner, if you change M to a sphere, they can tell you how many smooth structures there are on a sphere. For hyperbolic manifolds, we don't have a very good understanding.
But do you know if it's finite?
It is finite, and we'll see why shortly. Yeah, yeah. Okay, so an example. So now let me give a simple example to show that, well, sometimes these can be equal. So this is an example where M connects some sigma is diffeomorphic to M. So the starting easy observation is that if M is non-orientable, then M connects some sigma is diffeomorphic to M connects some sigma with the opposite orientation. This is entirely analogous to something hopefully familiar from like surface topology, that for surfaces, if you take the torus, connect some RP2, this is diffeomorphic to RP2 connect some the Klein bottle. And the reason, let me just remind you of the reason briefly. So RP2 is here, and you get the RP2 connects some to the torus by attaching a handle. Yeah, so you would, sorry, if you, okay, so here's two pictures. So this is a picture of RP2 connects some the torus, and this is a picture of RP2 connects some the Klein bottle, where the thing to pay attention to is the direction of the arrows. And these are the same because, well, there's a, I mean, RP2 is non-orientable. So what you do, you drag this handle along a path that switches the orientation, then this, oh, maybe I should write it this way. This oriented little loop becomes that one along that path. Okay. Okay. So this is just that fact in higher dimensions. So then, okay, so that's just the starting observation. So then, if sigma connects some sigma is different from Sn, which is to say that sigma doesn't have order 2 in theta n, which happens plenty of times, then M connects some 2 sigma. This is the same as, so M connects some sigma bar connects some sigma. And then sigma bar is the inverse of sigma. We mentioned that yesterday, so that's diffeomorphic to M. Okay, so, and 2 sigma by assumption is different from Sn, so this is an example. I guess it's 2 here, but okay. So connect some with an exotic sphere does not always change the smooth structure. That's the upshot. There are examples where M is orientable. If M is orientable but not smooth, or sorry, not spin, then you can construct examples. Yeah. Maybe I'll say more about that a bit later. And maybe I also said something about that last time. Okay, so, right, so it turns out that to understand this set of smoothings, it's helpful to first consider a weaker equivalence relation than diffeomorphism, which is concordance. So let me tell you how that's defined. So 2 smooth structures M0 and M1 on M are concordant if there exists, and I'm just going to draw a picture of the object. If there exists a smooth structure on the product, M times the interval, which restricts to the given 2 smooth structures on the boundary components. Okay, so that's what it means to be concordant. And we'll define the well, S of M will denote smooth structures on M up to this, up to concordance. So concordance gives you an equivalence relation, which is easy to check. Okay. And this SM will be easier to understand, but still not easy. So one remark is that there's a surjection right. In general, concordance implies diffeomorphism. So there's a surjection, there's a forgetful map from S of M to M of M. Okay, this fact follows from the H-cobordism theorem. So it holds in dimensions at least 5. Okay, and then one example, which will be an example and an exercise. For the sphere, this smoothings up to concordance on the sphere, this is isomorphic to theta n. So let's just remember how this is defined. So remember, theta n was defined as smooth homotopy n spheres oriented up to orientation preserving diffeomorphism. And yeah, so this is n at least 5. So for example, you could see that this map, okay, yeah, so there's a map in one direction because, well, if you have a smooth structure on the sphere, I mean, it is in particular a homotopy sphere. This map is surjective. Last time I mentioned that a result of Smale tells you that a homotopy n sphere is homeomorphic to the n sphere. So if you have a smooth homotopy n sphere, you in particular have a smooth structure on the topological n sphere. So that gives you an element here. And then it's slightly more complicated to explain why the map is injective. But I'm going to put that in the exercise with some hints. So, right, now let me tell you why this smoothings up to concordance is more tractable in terms of computations. So that's the content of, so that follows from what's called the fundamental theorem of smoothing theory. So this says there exists a space which is called, well, which is denoted top mod O, such that for every n manifold M of dimension at least 5, there's a bijection between these smoothings up to concordance and homotopy classes of maps into this space top mod O. Okay, so let me explain why this is so good, why this is very helpful, and also answer Misha's question. So first an example. If M is Sn, then this tells you that, so then we have homotopy classes of maps from the n sphere into top mod O, which is just pi n of top mod O. And that's isomorphic to theta n. And well, in particular, this is for n at least 5. So this doesn't really help us understand the smoothing so much, because we sort of already have that over here. But it does give us a little bit of information about this mystery space top mod O. At least tells us the homotopy groups in dimension at least 5. And in particular, Cravair and Milner show theta n's a finite group. And so these are finite. And in fact, in low degrees, the homotopy groups are also finite. So one corollary of this is, so for any M and dimension at least 5, this SM is a finite abelian group. Oh yeah, and moreover, it's the zeroth cohomology of a generalized cohomology theory. Which is a long way of saying there are ways to compute with it. Okay, I mean, if you have this, then like there's a spectral sequence, which part of it will converge to computing this thing, and and this is So this is tied up in the fact that this space top mod O is an infinite loop space. Okay, any questions about the statement or any of the setup?
Do we know the lower homotopy?
Yeah, right. So for n MO6, the pi n of top mod O is the same as pi n of k z mod 2 z3, which, okay, sorry, that's maybe as maybe an obnoxious way to write it. But that's just to say they're all 0 except in degree 3, it's z mod 2. So, okay, yeah, I'm not going to keep this up. So it's z mod 2z for n equals 3, and it's 0 for n at most else, and at most 6. Okay. Yeah, other questions? So let me give you some example. Let me do one example computation where we can understand more or less everything. When m is Tn, then using this theorem, you can compute. And what you'll find is that these smoothings up to concordance is isomorphic to this group. Okay, so the homology of the torus with coefficients in these finite abelian groups. And you can even describe explicitly generators. So this structure set is generated by.
Sorry, Ben.
Yep.
I think it's by n minus k of total.
Yeah, I think I'll be using like point grade duality and universal coefficients. I think this is okay.
It's just for k equals 0, you should get h naught of
Oh.
by, say any 7, you get pi 7.
Mm-hmm. Oh, pi 7. Oh, n minus k.
H k by n minus k.
Okay, yeah, you're right. Well, okay, let me give you the explicit so it's generated by smoothings of the form like this. So you take a k, k torus, connect some with a homotopy k sphere, and then product up to get the right dimension. And this would be a an exotic smoothing of Tn. This is almost true, except for the fact that pi 3 of top mod O is z mod 2z, which doesn't correspond to connect some with a homotopy sphere. This corresponds to changing the PL structure. But okay. All right. So the example we really care about is when M is a closed hyperbolic manifold. And in this case, well, yeah, I'll just say that this group, well, it's still not very much is known about it, so it's poorly understood. It's hard to compute exactly, but we can understand some things. So let me state a proposition. So if M is stably parallelizable, which is just to say that if you take the tangent bundle and add a trivial bundle, then this bundle is trivial. Then well, okay, so there's a map, is in fact a homomorphism, which sends from smoothings on Sn up to concordance to smoothings on your manifold, which just sends a homotopy n sphere to M, connects them with that homotopy n sphere. And the statement is that this is injective. So if you have a non-trivial homotopy sphere, M connects some sigma will at least be not concordant. Oh, I don't have the definition up anymore. Is at least not concordant to M, the standard smoothing. Okay. Are there any questions at this point?
What's the difference between non-concordant and non-diffeomorphism?
Yeah, so concordance implies diffeomorphism, but not conversely. So a concordance is in particular in H-cobordism, which tells you that any concordance is diffeomorphic to a product. So the ends are diffeomorphic. But the converse isn't true. So for example, you could see that in this example. So you have an action of the mapping class group of the N torus on these on this set, Tn. Essentially just precompose with action on Tn, and in here you have SLNZ. And this action is basically the action on cohomology. Okay, let me try to say this in a simpler way. In choosing these smooth structures, you choose a homology class, a k-dimensional homology class. But if you choose a different k-dimensional homology class, you'll get something that's diffeomorphic because it has the same expression. But it won't be concordant because they're different homology classes. Okay, so concordance implies diffeomorphic, but diffeomorphic things are not necessarily concordant. Okay. So in terms of our ultimate goal of finding exotic negatively curved manifolds, this tells us at least if M is stably parallelizable, we can get things that are smoothings that are not concordant to the standard smoothing. But that doesn't necessarily imply that they're not diffeomorphic. Okay. I feel like I should write it. Concordant implies diffeo. Maybe it's already on the board. But of course, not concordant doesn't imply not diffeo in general. And so we'll have to tackle that. We'll tackle that in the next lecture. Okay. Okay, good. Other questions, comments, concerns? Say again?
What about the proof of this proposition?
Yeah, so we can discuss the proof. Yeah, we can do that. Okay, so let's call this map phi. So the first observation, I'm just giving you a sketch. So the first fact is that phi is induced by a degree 1 map from M to the sphere. So you collapse the complement of a ball to a point. That gives you a map to the sphere. And then phi is induced at the level of, so then that induces a map like this. And this is phi. So you have, like, whatever this map is, collapse map C. So the claim is that phi is C star. Okay. Yes, so I mean, the proof is going to go through this fundamental theorem of smoothing theory. And so what we want to do is construct a left inverse. We want to show the map's injective, so we want to map in the other direction. Okay, and it's not so hard to do that. Let me explain how you get such a thing. So first, you can choose a Whitney embedding. From M into R2N. And because M is stably parallelizable, the normal bundle of this embedding is trivial. So you get an embedding like this. So here we've used the M as stably parallelizable. And then this induces a map of one-point compactifications. So then you get a map from S2N, which is the one-point compactification of R2N, to the n-fold suspension of M. Okay, so this is the embedding. This is like the dual map. Okay, now we're almost done. Right, we need to use one more, so we can finish as follows. So first of all, top mod O is an infinite loop space. So we could write it as loops n of some space y. And then, so in a way, this last part is kind of just a computation. I mean, it's not a hard computation, but let me just say how it goes. Oh, I don't want top mod O. I'm going to put y here. And then by the adjunction, this is maps from M to top mod O. And here, This is maps from Sn to top mod O. Okay, so, and then you check that this is a left inverse to the map that you started with, which is not so hard given the geometric construction of both of these maps. Okay, all right, so that's just, it's a little bit of algebraic topology once you have the Whitney embedding. All right. Any questions?
Have you arranged for M to be stably parallelizable?
Ah, okay, yes, thank you. Okay, so let me finish with that. Yeah, at the very end, I have a challenge for you. So yeah, so stably parallelizability, so remarks. Yeah, I think I'm going to keep this part short, actually. So let me just remark, or oh yeah, I'll just state a theorem of Deline and Sullivan, which says every closed hyperbolic manifold has a finite cover, yeah, that's stably parallelizable. So it's virtually stably parallelizable. Okay, so many problems are solved by passing to a finite cover. At the beginning, it was putting a negatively curved metric. Here, getting the tangent bundle to be stably trivial. Right, so let me now turn to the challenge. Now, this will be the end. The challenge is to give a new proof of this theorem. And let me explain why I think this is something one should do. And, well, okay. So I think the odds are, for this audience, any proof you come up with will be a new proof. Because you just have to don't use Étale homotopy theory. Okay, no problem. And it would be even interesting to prove weaker versions using things a little bit more internal to hyperbolic geometry. So for example, stably parallelizable implies that the Stiefel-Whitney classes vanish. And it also implies that, that you're stably almost complex. So up to adding a trivial bundle, the tangent bundle has a almost complex structure. And yeah, so, and maybe the one result in this direction is due to Long and Reed, which says that, well, so it's a new proof that virtually W2 of M is 0. Yeah, I mean, W1 is just orientation. You just pass to a cover, that's fine. W2, this is more interesting. I think essentially you basically use that the fundamental group is residually finite. But then there's more things to do. So I think us hyperbolic geometers should be somewhat embarrassed that, you know, the Tal homotopy theorists probably look at us and say, like, after all, this is like from, I don't know, the 70s or something. After all that time, you haven't come up with your own proof. And so, yeah, I think that's something that should be done. All right, I'll stop there.